Hello, everybody. Here I am inside your computer instead of in front of you in class, but we're gonna finish up section 1.8 this way, because I don't want to get too behind because of all of the mishaps. So we started the section over a week ago, last Thursday, and then Friday was supposed to be the test, and then I got stuck in the traffic during the rainstorm and was late then. And we had the test on Tuesday instead when I had a flu, and I probably got you sick with a flu too. Sorry about that. If I'd known I had a flu, I would have just stayed home again. Um, and then yeah, yesterday I stayed home and today I'm staying home, but I am feeling better, but not all the way better, and I probably shouldn't be around you guys yet. Uh, so anyways, I'm gonna do it this way, talk to you through your computer instead of through the air, and first we're just gonna review section 1.8, the stuff we've already did, and finish up the stuff at the end that we haven't done, and then I'll go over the section 1.9 stuff as well. So, first of all, just to review some of the terminology that we just barely introduced at the beginning, uh, a transformation is just another word for a function or a mapping. These three words mean basically the same thing, uh, where you take an input vector and the transformation does something to it and gets you a unique output vector called t of x. Uh, and there's the domain. The domain here, I'm highlighting in orange. That's the set of all of the input stuff that you can plug in. And the codomain is the set of all possibilities that you can get, which is usually going to be R2 or R3 or R8 or something like that. And the range is the specific part of the codomain that includes your actual output vectors. So having a vector in the codomain, not the range, means that there's no value of x that makes t of x equals c. I said it's impossible. I'm going to clarify that a little bit. Like so, to say that a vector is in the codomain but not in the range, that means that t of x equals c is false for all x in Rn. Meaning there is no value of x that makes t of x equal to the c if c is in the codomain but not the range. So we had some examples here of the difference between the codomain and the range. You can look over those again. With this one, if f of x1, x2 equals x1 squared plus x2 squared, the actual outputs that you get from this are only zero or positive numbers. So that's the range, that's the subset of R, but we still say the codomain is R. And we use the codomain just as a way of describing the kinds of things the outputs are. Like when we say f from R2 to R, that means that the outputs are going to be numbers. And that, so we're just describing the kinds of things you get as outputs, but it doesn't mean that all of the actual real numbers are outputs. So, and yeah, you can define a transformation by t of x equals ax, and that's the kind of thing we look at mostly in this class. And we defined a linear transformation here. This is my definition here, and the book's definition breaks it up into two separate statements, but they mean the same thing. You can use either one of these as the definition for a linear transformation. But if you use the second one, then sometimes if you're going to prove that a transformation is linear, this just means you have to do two separate things. But a lot of the time, you could make your proofs a little bit shorter by using this one. So, yeah, we saw how it works if you have not just two vectors in your linear combination, but a linear combination of a bunch of things. You can break that up into the corresponding output linear combination. And yeah, we proved in class that the only R to R functions that are linear are f of x equals mx for any number m. That will make you a linear transformation. Okay, so let's go on to this kind of thing here. We say that if A is an m by n matrix and u and v are vectors in Rn and C and D are in R, I didn't say D is in R here, but you can tell, hopefully, then this is just a fact from chapter 1. I don't remember I think this is in 1.4, algebra rules for matrix multiplication. Now, so in other words, if you do a linear combination before you multiply by the matrix, you get the same corresponding linear combination out after you do it. So that means that this linear transformation is linear. Remember, this is another notation for saying t of u equals just a times u. And what we have on the right here, this is another way of writing t of cu plus dv, and that turns into all this other stuff. And on the, I guess got right mixed up with left. This is the left, by the way. On the right, we have c times t of u plus d times t of v. So that just means that this transformation, which you can either give it a name like t and write it this way, or you can just say you input vectors u and the output is a times u. It means the same thing. Okay, so now let's talk a little bit about lines. Lines are important in linear algebra. So we talked about this before in section 1.5 a little bit. A line in Rn through the point P parallel to V is the set of points that we write P plus T times V, where T can be any real number. So it's kind of like starting at the point P plus, and then you can go in the direction of V as far as you want, backwards or forward, depending on what T is. If T is positive, you go in the same direction as V from P, or if T is negative, you go backwards. So if you plug a point like that, some point on the line, into this linear transformation, here's what you get. You plug in P plus TV, but because we're assuming that this is a linear transformation, you can do the linear combination in the codomain and get the same result. So you can do t of p plus little t times the transformation big T of v, and it should be the same vector result. So what does that mean? It means the set of images of points on the line. Remember, images is another word for outputs. The set of outputs of points from a line forms a line in Rm through T of P and parallel to T of V. So that means linear transformations map lines to lines. And if you're using the terminology of the 3 blue, 1 brown videos, he likes to talk about everything in terms of movement. That means that if it's a linear transformation and you plug in points on a line like this, sorry, I just paused it to draw for you, then the transformation will take points on a line, and after it moves them around, you will get points on another line in the codomain, specifically in the range. So it keeps lines in place. That's sort of what makes them linear in some sense. And so we're going to use that fact here in a minute when we do example 6. Let's look at example 5 here. This matrix 1, 0, 0, 1 is called an identity matrix. If t of x is defined as I times x, let's find t of 2, 5. So t of 2, 5, this is another way of just writing t of the vector 2, 5. Those mean the same thing. And this is defined as 1, 0, 0, 1. That gets multiplied by 2, 5. And we do the usual rules for multiplying a matrix times a vector. We're going to do 2 times this first column, which gets you 2 times 1, 0, plus 5 times the second column, which is 5 times 0, 1. And that becomes 2, 0, plus 0, 5. And that is also known as 2, 5, which of course is also known as the point 2, 5. Just different ways of writing the same thing. So in other words, this transformation doesn't do anything. It just gives you the same output that you plug in. So you can call this the identity transformation if you want. But we're going to be talking a lot about identity matrices as we go on. So anyways, let's look at if we define t of u equals a times u, and this is your a, what is the image of the unit square under t? So we're going to try to get a nice picture of this here. So this is what I mean by the unit square. It's the 1 by 1 square with these 4 corners in R2. And it does include the edges and the endpoints. So 1, 1 is part of the unit square. So is 1, 0.5 right here, etc. So when we say what is the image of this, we mean what is the set of outputs that correspond with these inputs. Where is this transformation going to move the square, in other words? What is it going to transform the square into? So we could start by just finding t of some points. We could just do t of 0. Well, actually, t of 0 is equal to 0 for any transformation, any linear transformation. So that's good. What about t of the vector 0, 1? Well, we're going to do this matrix A times that. You might want to pause it here and just get a little practice with this stuff by yourself. And then you can fast forward later to check your answers. Some luxuries of video lectures. But t of 0, 1 is going to be, well, we're going to do 0 times the 1, negative 2 vector, and that plus 1 times the 0, 1 vector. That just gives you 0, 1 as a result. We can do t of 1, 0. T of 1, 0, we're going to take the 1 times the 1, 2, 1, negative 2, plus 0 times 0, 1, and that will give us 1, negative 2 plus 0 is 1, negative 2. And we can do the same thing with t of 1, 1. And we'll get 1 times the first column of A, 1, negative 2, plus 1 times the second column of A, 0, 1. And So that's going to give you 1, -2 plus 0, 1, which will come out to be 1, -1. Okay, so what do you do with that? I mean, that tells you 4 points that are in the image of the unit square under t. These are 4 important output points. But what will happen to the rest of the points? Well, let's see. Let's try to start graphing it. So what I have here, I just graphed the 4 output points I know about, and I want to think about where the rest of them will go. Well, first of all, let's think about lines. All of the points on the y-axis here between 0 and 1, those are all points on a line, and we just talked about how linear transformations map lines to lines. So all the points on this line are just going to get moved to another line. And I already know 2 points on that line. There's t of 0 is 1 point on that line, and t of 0, 1 is another point on that line. So this must be the line that all of these points get moved to over here. So all of those points end up right there. And then how about all the points on this line between 0, 1 and 1, 1? Well, they are all going to get moved to some line over here, and I already know what 2 points on that line are. There's t of 1, 1 is right here, and t of 0, 1 is right here. So the rest of those points should be on that line. Likewise with the other lines, all the points from between 0 and the 0 vector and the point 1, 0 are all going to get mapped to that line, and all the points on the line from 1, 0 to 1, 1 will all get mapped to this line. And then all the points in between are also on some line between these points. So for example, all the points on a line, let's say from here to here, from 1 point on the line on the left to another point on the line on the right, if you make a line between those 2 points, those are going to have to go on a line from here to here. So they're going to end up on like that kind of line. And all the points on a line from here to here are going to end up on a line in the output space from here to here. So you can do that with all the points in between, and you can see that the set of outputs that you get are just going to be all of this stuff filled in. Like so. And that is the image of the unit square under t. And the name of this is a shear transformation. It is related to shear forces that you might have learned about in like an engineering class or maybe physics. It's also related to actual shears, meaning like scissors. So here's the Wikipedia page to explain what shear means in a little bit more detail here. They also talk about wind shear and like meteorology when they have hurricanes, for example. Wind shear helps stop hurricanes. Anyways, shearing forces are unaligned forces that push one part of a body in one direction and another in the opposite direction. So you can see an example of how that would push a rectangular thing right here into a parallelogram sort of thing, which is what happened with our example. And you could also see how that's related to actually cutting something with scissors. Scissors push one side of the paper in one direction, and then they push the other side of the paper in the opposite direction, and that's how you get a cut in paper or in hair or whatever else you're trying to cut with shears or scissors. That's enough of that. Let's get back to linear algebra and talk about a different kind of transformation here. So this is a transformation called P, which takes input vectors in R3 and gives you R2 output vectors. And it's defined by multiplying your R3 vectors by this matrix. Make sure that you are allowed to do this because if you have an R3 vector, it's got 3 entries, 1 for each of these columns. So let's do P of 1, 2, 3. So it's defined by doing this matrix 1, 0, 0, 1, 0, 0 times the vector 1, 2, 3. That's what this formula says to do. So we're going to do 1 times the 1, 0 plus 2 times 0, 1 plus 3 times 0, 0. And 3 times 0, 0 is just 0. You're going to get 1, 0 from this one. This one's going to be 0, 2 plus 0. That's just going to give you the vector 1, 2 when you add those up. Okay. So what it kind of did with 1, 2, 3 is it gave you an R2 vector which just didn't have the third component in it anymore. Let's do the same thing with XYZ. And the x times the 1, 0 is that, plus y times 0, 1, plus z times the 0 vector is just going to make it go away. So I'll show an extra step this time for, I don't know, no good reason. So that you see when you add these vectors up, you get x plus 0, and then 0 plus y plus 0 is the point xy. And so this is called a projection because it's kind of taking, let's see if I can draw a picture of it. So here is R3 is the set of all of these possible inputs, including inputs like 1, 2, 3, which I tried to draw right here, sort of. If you input that, the output that you're going to get is down here. And it wasn't quite in the right spot. There we go. So something like that. So it takes the third dimension and basically erases it and takes these things and gives you kind of like a shadow. That's the way you want to think of a projection, as a shadow. By the way, when you go see a movie in a theater, at least with a traditional film projector, this isn't true with digital projectors, but with traditional film projectors, what you're seeing on the screen is basically a shadow of the film. And that's what this does here. If you imagine like a light from above, all of the things in this line would all get transformed to the same point here. And so, yeah, that's one good example of a linear transformation. Let's do this example. Now, when we say is B in the range of this linear transformation, that's the same thing as asking, is B equal to t of x for some x? Just to reiterate this again with different notation, the range is the set of outputs that you get, the set of all possible t of x's for any x in R4. So you could also write that in terms of a times x, because t of x just means a times x. So you could write this as the set of vectors of the form ax such that x is in R4. And now if you want to know is B in that set, what we want to know is B equal to A times X for some X in R4. So you could well, first of all, we want to know, is this equation true? Does this have a solution? So we could write the augmented matrix of this equation, which is going to be 3, 1, 0, 1, 2, 0, 1, 4. I just paused it so you didn't have to hear me listing off all the numbers. But anyways, this is the augmented matrix that corresponds with this matrix equation. And we want to know if this has a solution. So we're just going to row reduce it and see if we end up with anything non-zero in the other thing. And you could row reduce this by hand if you want some practice. You could pause it now to do that. Or I could just do it on FreeMat for you right now. Here's what I got when I did it in FreeMat. And we can see that it's possible to make this first equation work. This first equation says x1 plus 0, x2 plus 2x3 minus 4x4 equals 0. That's fine. The second equation you could make work, but the third equation here would be 0 equals 1. So there's no way to make 0 equals 1, which means there is no way to make b equal to t of x. So the answer to this question is no. So I just wrote out that answer here in a little bit more detail. All right, so I'll make another video next about section 1.9. And you can email me if you have questions, or post them in Canvas is actually the best thing. If you just post it in the Canvas discussions, that way other students can answer it, and then they'll be getting better at linear algebra too as they try to answer your questions. And yeah, so we'll keep on trying to learn over the internet. Have a good rest of your weekend or whatever time of day it is there.